Okay, everyone. So today we are going to focus on the center of mass proofs. Okay, so there are 6 proofs in your syllabus. The center of mass of a semicircular arc, center of mass of a semicircular lamina, center of mass of a solid cone, center of mass of a solid hemisphere, center of mass of a hollow cone, and center of mass of a hollow hemisphere. So today we are going to focus on all these 6 proofs. Okay, so let's start. Center of mass of a semicircular arc. Okay, so it's an arc. It's all about the length. Okay, it's all about the length. So let's focus on that first. First of all, we have to focus on the symmetric idea. Okay, so there are two main axes in this case, x-axis and the y-axis. So as you can see, you can clearly see x-axis is the axis of symmetry here, right? So we have to write that. Okay, we have to write that down first. Okay, you will get marks for that. So by symmetry, the center of mass is on the x-axis. So what's that supposed to mean? What that's supposed to mean is y bar is going to be 0. So we are not going to focus on the y bar, y coordinates. We are going to focus on only the x coordinate. Okay. Now we are going to define something called rho. Okay. So rho is going to convert the length into the mass. Okay. So let rho be the mass of the unit length. Mass of the unit length. So this is the technically the conversion of the length to mass. Okay. Unit length. Okay, let's jump into the length. So length of the semicircular arc. What is this? This is a half circle, right? So circle circumference is 2 pi r. So the half circle is half into 2 pi r, which is pi r, right? Okay, so the semicircular arc length is pi r. So now let's use that rho. So mass of the semicircular arc is pi r into rho. Okay, so this is the first thing we need, capital M, the mass of the whole object. Okay. Okay, now let's focus on the elemental arc. Elemental arc is the component that made this whole arc. Okay, the tiniest little component that made this whole arc. That is called an elemental arc. So first of all, we have to define an elemental arc. Look at this. Look at this. You can clearly see this whole arc can be represented by parts of arcs, right? Parts of small arcs. So we are going to only focus on one part. Okay, here we go. First of all, let's take y-axis and let's think that this is r radius. Now I'm going to design elemental arc. Okay. Yes, it should be very tiny little arc, but the thing is, like, to give you a best representation, I'm going to take like a big chunk of part. Okay, so this is that elemental arc I'm going to talk about. Okay, now let's define some things. Let's take this small angle, this small angle as d theta. So you know that this is r. According to radian measures, you know that the length of an arc length can be calculated using L equals r theta. Theta should be radians, right? So in this whole question, theta is going to be radians too. So r into d theta. That's the length of this small elemental arc. Got the idea? Okay. So that's it. Now let's write. Length of the elemental arc is r d theta. So now we are going to convert the length into mass again. So it's r d theta into rho. Okay. Look at this. We design capital M and we design simple dm. Now we are going to focus on this. Horizontal distance to the center of the mass of the elemental arc from the origin. Okay. Now here we go. Now you can pick any place as the center of mass of this elemental arc, because why? elemental, it's tiny, it's little. Okay, so you can take anywhere you want. So to keep this diagram very clean, I will take the center of mass here. You can take the center of mass here also, it doesn't matter. Okay. Okay, so I will take the center of mass right here. So that is the G, right? Okay. Now let's now let's calculate the horizontal distance. Okay, so this is the hypotenuse. So this is the perpendicular distance. So now we need what? The distance, the horizontal distance of the center of mass and the origin, okay, and the center. So this is it. Now let's put this as theta. So this is going to be r cos theta, because why? This is also going to be r, okay. So that is r cos theta. Now that's it. So that's the horizontal distance to the center of mass of the elemental arc from the origin. So let's take r cos theta here. Done. So now we have capital M, simple dm, and simple x. That's it. Now let's go to the definition. The definition of x bar is integrate from a to b x dm over m. We know x, we know dm, and we know capital M, but we don't know what is a and b. It's like this. Look at this. When we take the elemental arc, we define something called theta, right? So when the position changes of the elemental arc, the theta changes, right? So theta actually is the main variable in this question. So look at this. Theta changes from 0 to 90 as well as minus 90. So that's the two boundaries we need for theta. So theta can be minus 90 to plus 90, right? So when we are writing 90s, we are writing pi over 2s, because why? We have to stick to the radians now. Okay, so let's write integrate from minus pi over 2 to plus pi over 2. X is r cos theta. What is dm? We found everything, right? Don't worry. So it's r d theta rho divided by, what is capital M? It's r pi r rho. Now that's it. Now, the next step is take all the constants out. Okay, so r squared is a constant, take it out. Rho is a constant, take it out. Now you will end up with these two. Cos theta d theta and divided by pi r rho. Now what happened? We can cut all the constants, right? So 1r cuts 1r, rho cuts rho. So you will get r over pi. Now look at the integration part. It is not that hard, it seems, right? Yes. What is the integration of cos theta? It is sin theta. Nice, good. So sin theta minus 90 to plus 90. Most of the people think that the integration part is hard when it comes to the proofs of center of mass. No, it's not. Okay. So r over pi. Sin 90. Sin 90 is 1 minus sin minus 90 is minus 1. So 1 plus 1 is 2. So the answer is 2r over pi. Got the idea? So yeah, that's it, right? So the answer is 2r over pi. So now we can conclude that the center of mass of the semicircular arc of radius r is 2r over pi from the center. From the center. That's it. So this is the center of mass of a semicircular arc. Okay. Now let's jump into the semicircular lamina. Lamina is all about a surface. Okay. So when it comes to surface, it's all about area. Okay. So before we jump to those parts, let's go to the symmetric part. Okay. So again, let's define x-axis. Okay. Let's define the y-axis also now. 1. So let's say this is R, this is R. Okay, by symmetry, the center of mass is on the x-axis, right? Therefore, y bar equals 0. Now, it's all about area, I told you, right? So you have to take like this row. Let row be the mass of a unit area. Okay, not unit length now, it's unit area. Okay, so this row will convert all the areas into mass. Okay, only you have to do is multiply by row. Okay, so this is a semicircular. Now let's finish the capital M part, the whole object mass, right? So this is a semicircular. Semicircular means half circle, right? What is the area of a circle? It's pi r squared. So half of a circle is half pi r squared, right? So area of the semicircular lamina is half pi r squared. Now let's multiply that by rho, right? So that will convert the area into mass. So capital M is half pi r squared into rho. Very easy. Done. Okay. Now, what is the elemental sector? Here, it's not arcs, it's sectors, right? So you can clearly see this total lamina can be separated into several sectors, right? Okay, so now we are only going to focus on one sector, that is called elemental sector, right? Actually, when you take this, you can clearly see this is not going to be an elemental sector. Okay, actually, it's going to be elemental triangle basically. Because why? Since this is a very small area, very small sector, we assume that the sector is going to be a triangle. Okay, so yes, we are telling it's elemental sector, but we are going to stick to the triangles stuff. Okay, now let's say this is R, this is R, so this is d theta. So what is the area of elemental sector? You know that in radian measures we can use half r squared theta. Instead of theta, we are using d theta. Okay, now we are going to multiply that area by rho to make it into a mass. Okay, now horizontal distance to the center of mass of the elemental sector from the origin. Okay, now I told you this is going to be considered as a triangle, no? So you know that triangle has a different center of mass, right? So where is it? It's actually on this median line, right? You know that, right? How far? It's taking as 2/3 of R. You know that, right? So center of mass of a triangle lies on a 2/3 of the median from the vertex. Okay, so it's 2/3 R. Now let's take that triangle. So now we are going to focus on this area. That's the horizontal distance between the origin and the center of mass of the elemental sector. Now again, let's take this as theta. Now it's not r cos theta because it's not r now. It's actually 2/3 r cos theta. So it's 2/3 r cos theta. Okay, now we have all these three. You can clearly see this on the board. Again, we are going to do the question from -90 to +90. X is considered as 2/3 r cos theta. dm is considered as half r squared d theta rho. Then divided by m. M is half pi r squared rho. Okay, now let's stick to the integration part. So as usual, we are going to take all the constants out. So 2/3 out, half out. 2/3 into half is 1/3, right? So 1/3 out. R cube is out. Then rho is out. Okay. Then we have the integration part only, -90 to +90. Still, we have that cos theta, d theta with us. Okay. Then divided by 1/2 pi r squared rho. Let's cut the constants. Rho cuts rho. R squared cuts r squared. Now you can clearly see 2 goes up, 3 goes down. So it's 2r over 3 pi. Now look at the integration part. Integration part is cos theta, right? So what is the integration of cos theta? It's sine theta from minus pi over 2 to plus pi over 2. So look at this. It's 2r over 3 pi. Sine pi over 2 is 1 minus sine minus pi over 2 is minus 1. 1 plus 1 is 2. 2 into 2 is 4. So final answer 4r over 3 pi. Done. Very easy. So we can conclude the answer now. Center of mass of a semicircular lamina of radius r is 4r over 3 pi from the center. So this is the proof of center of mass of a semicircular lamina. Okay, now let's focus on the center of mass of solid cone. Okay, so it's a solid, so it's all about volume, right? Okay, now first of all, let's stick to the symmetry part, right? So as you can clearly see, again, the axis of symmetry will be x-axis, right? So by symmetry, the center of mass is on the x-axis. Therefore, phi bar is 0. Okay. Now it's all about volume, I told you, right? So let's define rho as this. Let rho be the mass of a unit volume. Done. Now let's take the volume of the solid cone. Now we have to define something else. So this is y. So let's define this as the radius and this as the height of the cone. We need these two, right? So now we can write volume of the solid cone is 1/3 pi r squared h. This is the volume of a solid cone. Now let's multiply this by rho. So you will get 1/3 pi r squared h into rho. That will be the total mass of this solid cone. Okay. Now what is the elemental disk here? Why it is called an elemental disk? You can clearly see, you can cut this volume into several disks, right? Because why? It's a solid, no? So when you separate into several parts, those are going to be tiny little disks. Okay. Yes, the radius is getting changed, but those are disks. So disk means it's a cylinder, right? It's a very thin cylinder. So that will be our elemental mass here. So technically it's a disk. Okay. So I'm not going to draw a small disk. You know that, right? So to give you the best idea, I will draw something bigger. Okay, now look at this. Rather than drawing these slant lines, I'm going to draw a perfect cylinder. Because why? We have to assume that this is a volume question, no? This is a solid disk, no? So we have to assume that the whole mass is spread, it's distributed along the volume, right? So we can reduce that, minimize that error, okay? Now we need more data. Okay. So since this is a disk, you know that the center of mass is at the center of the disk. Okay, so let's put it here. Actually, it's like here. This is the cylinder. It should be here, but since it is defined as a very thin disk, we can mark it anywhere. Okay. So now let's take this as y. It's the radius of the elemental disk. And let's take this as x. Now our plan is writing y in terms of x. So to do that, we are going to use something called similar shapes. It's actually a grade 7 lesson. Okay. So look at this. Look at this triangle. Look at this triangle. This is symbol R and symbol H. That is actually this triangle, right? Okay. Now I'm going to focus on this triangle also. Okay. this triangle and this triangle are known as similar triangles. Got the idea? Okay. So let's draw that triangle also. So this is y, this is x. Now, from similar shape theory, you can clearly write y over x is equals to r over h. So now you can write y as rx over h. Got the idea? So we can substitute y in terms of r now. Got the idea? So that's the whole idea of getting the y, but writing in terms of x. Now let's go to the volume of elemental disk. So it's a cylinder, right? What is the volume of a cylinder? It's pi r squared h, right? So it's pi r squared h. Now we have to take h as dx, right? It's a very, very tiny little distance, right? So that's why it's called dx, okay? So pi y squared dx. Now we have to remove y from this equation. So we are going to use rx over h. So it's pi rx over h squared dx. Got the idea? Okay, now since we have the volume, let's multiply it by rho to make it mass, right? Okay, so pi r squared x squared over h squared dx, that's the volume of the elemental disk, then multiply by rho again to make it a mass. Done. So now we have everything. Now horizontal distance to the center of mass of the elemental disk from the origin. Yes, it's just x, right? Yeah. No need to worry about anything. That variable is the x. So let's put x. So x is x now. So we have everything now. Let's fill in the blanks now, right? Okay. Now what is the limit of x? Look at this. X starts from here and all the way come into here, right? That's all. When the disk changes, their distance also changes, right? Their distance also changes from 0 to what? From 0 to h. H is the maximum mark, 0 is the minimum mark, okay? So that's the limit. Now let's write integrate from 0 to h, x is still h, dm is pi r squared x squared over h squared dx rho divided by what is the mass? Mass is 1/3 pi r squared h rho. Okay, done. Now let's remove all the constants out. So pi is a constant, r squared is a constant, rho is a constant, and h squared is a constant. Then divided by 1/3 pi r squared h rho. The integration part is 0 to h x cube, right? Yeah, just x cube dx. So integration part is not going to be hard, okay? Yes, now let's cut all the constants. Pi cuts pi, rho cuts rho, r squared cut r squared, okay? So what is the remaining part? 3 goes up, right? Yeah, 3 goes up and h squared comes down. So it's 3 over h cube. Got the idea? So what is the integration of x cube? It's x4 over 4 from 0 to h. Now let's substitute h. So 3 over h cube, h 4 over 4 minus 0 4 over 0 over 4, which is 0, right? So final answer 3 over h cube multiplied by h4 over 4, which is 3h over 4. So that's the answer. Now there's a small problem in this. It's all about the paper. Paper will ask this answer in two different styles. I will tell you what is that. Okay. Now look at this cone. So Look at this. Now we found something. No, we found that this is going to be 3h over r. That's okay. 3h over 4. That's the center of mass. So what is this part? This is 1h over 4. So this is called the vertex, and this is called the center of the base, right? So you can write the answer in two different styles. Okay, totally depending on the paper, but I will write this. I will write these two methods here. Okay, so you can pick one of them according to the paper. Center of mass of a solid cone of height h is 3h over 4 from the vertex. From the vertex, or you can write h over 4 from the center of the base. From the center of the base. That's it. So let's go to the center of mass of a solid hemisphere. Yes, that is also regarding a elemental disk. Okay, it will be very easy. Okay, let's jump into that now. Okay, now let's focus on the center of mass of solid hemisphere, right? Okay, so first things first, symmetry. So this is the x-axis and this is the y-axis. So by symmetry, the center of mass is on the x-axis. Therefore, y bar equals 0. Done. Now so still it's a volume question. So let rho be the mass of unit volume. It's all about volume. Okay, now let's take this R, this as R, volume of the solid hemisphere. Yes, volume of a sphere is 4/3 pi r cube. So half of that is 2/3 pi r cube. So this is 2/3 pi r cube. So let's multiply it by rho. That's how you convert volume into mass. So it's 2/3 pi r cube rho. So that's the total mass. Done. It's getting easier, no? Yeah, now let's define that elemental disk. You already know what to do. Yes, so this is the center of mass. This is the y. And this is the x. And the connection now coming from this. Who's this? The radius, right? Yeah, it's the radius. Look at this. Radius, radius, radius. It's the radius. It's the radius of the hemisphere, okay? So that will make you the relationship for y to the x, right? Okay, like the cone, we had to write y in terms of x. Now we are going to take that right angle triangle. When you see a right angle triangle, you know that it's going to be Pythagoras, right? Okay, so r was there, y was there, and x was there. Okay, so it's r squared equals x squared plus y squared. So you can write y squared as r squared minus x squared. That's enough. Okay. Now let's design the volume of the elemental disk. It's a cylinder again. Now this is going to be dx again. Okay. So the volume of a disk is pi y, right? Pi r squared dx. Now we know y squared, right? Yes, we found y squared earlier. So now let's substitute that pi. Instead of y squared, let's write r squared minus x squared dx. Here we go. Pi r squared, sorry. Okay, pi r squared minus x squared dx into rho. So that's going to be dm. Very easy. Okay. Yes, it's all about writing y in terms of x. Now the x is x. It doesn't matter now because it's already defined. Now x is going from where to where? X is going from 0 to r, right? Yeah, r is the maximum point. Now let's integrate. Integrate from 0 to r, right? Yeah, r. X is x. Dm is pi r squared minus x squared dx rho divided by 2/3 pi r cube rho. Now that's it. So let's stick to the integration parts now. Guys, let's get the constants out. So pi is coming out, rho is coming out. In bottom, in the denominator, we have 2/3 pi r cube rho. Now look at the integration part. X and r squared minus x squared dx is inside. Now let's cut these constant. Rho cuts rho, pi cuts pi. 3 goes up, so it's 3 over 2r cube. Integrate from 0 to r squared x minus x cube dx. All right, now let's integrate this very quickly. Shall I do this here? So 3 over 2r cube. Look at this, r squared is a constant. So x can be integrated, x squared over 2 minus x cube can be integrated to x4 over 4. Integrate from 0 to r. So it's 3 over 2r cube. R squared into, now we are substituting this. So r4 over 2 minus r4 over 4 minus 0. It's a lengthy one, no? Okay. So 3 over 2r cube multiply r4 over 4. So when you cut everything down, you will get 3r over 8. Yes, that's the famous one, right? Yes. So the center of mass of a solid hemisphere of height is wrong, of radius r. Of radius r is 3r over 8 from the center. Yeah, so that's it for the center of mass of a solid hemisphere. Okay, now the center of mass of a hollow cone. Hollow means no volume, right? So it's all about area. It's all about surface area. Got the idea? Okay, think that now. Okay. Now what is this? X-axis. What is this? Y-axis. By symmetry, the center of mass is on the x-axis. Therefore, y bar is 0. Let P be the mass of what? Of area, right? Because now we are going to stick to the areas again, right? So let rho be the mass of unit area. Rho is the converter between area into mass now, okay? Surface area of a hollow cone. You know that. So first of all, we have to define a letter R and another letter, that is slant height, right? Yes, because why? You definitely know this from grade 7 or grade 8. The curved surface area can be calculated using pi r L, not pi r h or something, right? Pi r L. So the mass of the hollow cone will be pi r L into rho. Done. Okay. Surface area of an elemental ring. What is elemental ring means? Yes, this is a hollow structure, no? So when you are taking a disc, no, it's not coming as a disc. It's coming as a ring, right? Okay. Another thing, when you are taking the ring, yes, you have to take the slant heights now, not like the earlier version, because why? The surface is, this is the surface area question, right? So mass is distributed along the surface, okay? So you have to focus on the surface now. You can't change the surface now, right? When you change the surface, it changes the mass definitions, right? So let's stick to the slant distances, right? So let's take this small distance as dl. It's a small slant distance, dl. So according to that, I'm going to take something here. So that is going to be y, because this is the center of mass now. And now we need this also. What is that? That is the dx part. Okay. Now here's our dx. It's over there. And now we need another definition. What is this? The height of the cone. So, what is the surface area of an elemental ring? It can be written as this. It's a surface area, right? Remember the surface area of a cylinder. Surface area of a cylinder, I mean the curved surface, it's 2 pi r h, right? Grade 7. 2 pi r h. So, here 2 pi r is y. Now, instead of taking dx, now we have to take dl. 2 pi r h. Yes. Now we have to convert all the y into x's and the dl into x's too, because y, our variable, is x. So we have to define y and dl in terms of x. Let's jump into that now. Again, the theory will be similar shapes, similar triangles. Look at these triangles. This triangle, 1, this triangle, 2, and this small triangle. Again, big triangle, this medium version, and the small version. All those 3 triangles are similar in shape. So now we are going to take that chance to do this question. Look at this. Now this is the bigger one. It has L, R, and H here. So now I'm going to draw the smaller version, the medium version. In the medium version, we had y here and we had x here. Then I'm going to draw the smaller version. The smaller version will be dl here and dx here. Okay, let's write some things from here to here. So y over x can be written as r over h. That's the similar shape theories, right? So y over x is r over h. So y equals rx over h. So done. We know what is y now. Okay, let's keep it for later. Now let's go from here to here. You can clearly write dl over dx as L over h, right? So yes, dl can be written as Lx over h. Ldx over h. Fine, right? So now we wrote y and dl both in terms of x. Now let's substitute that here. So it's 2 pi. What is y? Y is rx over h. What is dl? Dl is L dx over h. Got the idea? Done. Now that's the surface area of the elemental ring. Now we are going to convert this elemental ring area into mass now. Okay, so shall I write it here? So dm equals 2 pi r l x dx divided by h squared into rho. So that will be the total mass. 2 pi r x l dx divided by h squared over h squared rho. That's it. Okay. So here x is still x, right? Yeah. Horizontal distance to the center of mass of the elemental ring from the origin is x. Done. Now let's stick to this plan. Okay. So x is now, where is x? X is changing from 0 to here, right? What is this? This is h, right? Yeah. So 0 to h, x into dm 2 pi r l x dx rho over h squared divided by pi r l rho. Okay, now let's do the integration part. Let's take all the constants out. 2 out, pi out, r out, L out, rho out, divided by h squared out, and pi out, pi r L rho is already there. So what is the integration part? Integration part is just x dx. Okay, x squared dx. I told you the integration is not the hardest part here, right? Most of the people thought that integration, because of integration, center of mass is hard. No, 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 no. It's not. Okay, because most of the people don't know the steps. That's what. Okay, now you know. Okay, let's cut pi r L rho cuts pi r L rho. Very easy. Now you ended up with 2 over h squared. So x squared is x cube over 3 from 0 to h, right? Okay. So it's 2 over h squared, h cube over 3 minus 0. So the final answer is 2h over 3. Done. So yes, we have a cone. So what's that supposed to mean? They are saying from the vertex, it's 2h over 3. Or you can write from the base, it's h over 3. So you can define either way. According to the paper, you can pick one of them. So center of mass of a hollow cone of height h is 2h over 3 from the vertex. Or you can write h over 3 from the base. Done. So this is the center of mass of a hollow cone. It's all about elemental ring. Okay, it's all about surface area. Got the idea? Okay. Okay, let's jump into the hollow hemisphere. First things first. This is the symmetric axis x. This is the y. R. Okay. So by symmetry, the center of mass is on the x-axis. So y bar equals 0. Let rho be the mass of the surface area, mass of a unit area. Why again area? Because it's hollow, right? So we have to stick to area. Now the surface area of a hollow hemisphere. Okay, you know the surface area of a sphere, right? It's 4 pi r squared, grade 7. So half of it is 2 pi r squared. So it's 2 pi r squared. So let's convert that into mass by multiplying by rho, right? So 2 pi r squared rho. So that's our capital M. Those are like 5-second stuff, right? Okay. Surface area of an elemental ring. Nice. Okay. Now let's define another elemental ring here. So from here to here and from here to here. So it's here and here. Now we are not going to do the disk stuff. We are going to do the elemental rings now. Okay. Now what? Okay. Now we are going to define more stuff now. So this is going to be y. So this is the center of mass here. So this is the x. So this is the r, right? Okay, now we need another version here to here. So we need d theta here. Therefore, this is going to be what? This is going to be r d theta, the length, right? Okay, we need that, right? Yes, good. Now, again, we need this theta to do some y. We had to write y in terms of x again. Okay, so let's finish that part first. Let's take that triangle. So every step has a meaning. Okay, so what is this? This is where we are writing x and y in terms of r and theta, right? Okay, now it is not going to be Pythagoras, because why? We have to write both x and y in terms of r now. Okay, because we are going to do the question like the earlier version. What is the earlier version? The arc version, semicircular arc and semicircular lamina version. That part. Okay, so let's write y. X as r cos theta, you know that. Done. Then y as r sin theta. Done. Okay, so surface area of an elemental ring can be written as, again, it's a curved surface area of a cylinder. So it's 2 pi r h, which is r d theta. Now let's substitute y with r sine theta. So r sine theta, r d theta. So the mass of the elemental ring will be 2 pi r squared sine theta d theta into rho. Done. Okay, now x is not x anymore. It's all about r cos theta, because why? We are going to change the variable now. In this question, most of the time it was x. Now it is going to be theta. Okay, so we are going to write every element, every part in terms of thetas. Okay, it's like substitution, integration by substitution. So we have to convert all the letters into one single variable. In this particular question, it's theta. Okay. Okay, now let's check the limit of theta. Okay, theta, it's already depending on the rings, right? The largest ring will get the theta as 90, and the smallest ring will get the theta as 0, right? So the boundary for theta will be 0 to r. Okay. So the boundary of the theta will be 0 to pi over 2. Now x is r cos theta. Then the dm is 2 pi r squared sine theta d theta rho, then divided by 2 pi r squared rho. Now let's take all the constants out, but I'm not taking these two out. I will tell you why. I'm taking everything else but 2. So r cube is coming out. Pi is coming out, rho is coming out, but who will stuck there? 2 sine theta cos theta d theta will be there. Then divided by 2 pi r squared rho. Now look at this. Pi cuts pi, rho cuts rho, r squared cuts r squared. So you will have r over 2 here. Now look at the integration part. Why I kept that 2 there? You know that 2 sine theta cos theta can be written as sine 2 theta, right? And now we can integrate this very easily. So r over 2, look at the integration part. The integration of sine is minus cos, right? Minus cos 2 theta. Then you have to divide by the derivative also, which is 2 from 0 to pi over 2. Okay, now let's substitute r. Okay, now 2 goes out. So r over 4 minus cos 2 theta from 0 to pi over 2. So r over 4. So guys, r over 4. Okay, cos 2 theta. Cos 2 into pi over 2 cos pi. Cos pi is minus 1. Minus into minus 1 is plus 1. Then minus cos 0 is 1. So it's minus 1 again. So it's going to be r over 4 into 2, which is r over 2. So we can write the center of mass of a hollow hemisphere of height, again, that's mistake, of radius r is r over 2 from the center. So we discussed all the 6 proofs you need. Center of mass of a semicircular arc, center of mass of a semicircular lamina, center of mass of a solid cone, center of mass of a solid hemisphere, center of mass of a hollow cone, and center of mass of a hollow hemisphere. Okay, so I think I hope that you got everything okay with this. Okay, so please study hard, study well, and do your exams well. Okay, I'll see you soon then. Okay, bye.